Hi kids, this is a slightly scratchy voiced Miss Nichols on our 20th video of the year. The topic is conservation of charge and charging. This is, I think, a pretty challenging series of topics. I would really encourage you to make sure that you leave the sound on to listen to my explanations and also to thoroughly go through this video because it kind of sets the foundation for this entire unit. The essential question for this video is, how do objects end up with an unbalanced sigma charge? In order to answer that essential question, we need to define a new variable called charge. Charge is one of the fundamental variables, so it defines objects in the universe, just like we would define an object based on its mass. We can describe things based on their charge. In an equation, the symbol that you'll see, or in a diagram, is a lowercase q. And the unit for charge is the coulomb, which is a capital C. You'll be responsible to know the variable symbol and unit of this next time you take a math proficiency test. A note that the vast majority of charged particles in our universe are protons and electrons. There are other charged things, but we're not going to be dealing with them in this class. So usually when we talk about charge, we're talking about how many protons or electrons an object has. Protons are defined as positively charged subatomic particles, and we're going to assume that each proton has a charge of +1. This is a little bit of a lie that you'll learn about later on, but for the purpose of this unit, it's fine to assume that each proton is +1 coulomb, and electrons are exactly opposite from protons as far as charge goes, so each one will be -1 coulomb per electron. Charge is a conserved property, just like mass and momentum that we learned about, and energy that we learned about earlier this year, which means that the total, or the sigma, charge in a closed system is going to be the same over time. In our universe, it turns out that there are exactly as many protons as there are electrons. This is some crazy coincidence that physicists are debating over the reason why this must be, but in any case, we know it's true. So that would mean that the total charge of our universe, or the sigma charge of the universe, is actually 0, because every +1 is canceled out by a -1. Another way to say this is the universe is neutral. Systems smaller than our universe might have a non-zero sigma charge, depending on what's happened to them. It's easy to find sigma charge in a system. You just add together all the charges of the protons, which are positive, and then take away all the charges of the electrons, which are negative. So if we had a system here of 4 protons and 3 electrons, the overall sigma q would be +1, because I added 4 and then I took away 3, which I would describe as a small positive sigma charge. Many systems, like our universe, have the same number of protons or electrons. For those systems, sigma q is going to be 0 coulombs, because we add 4 for the protons and then we take away 4 for the electrons. And as I said earlier, you might also describe this as neutral. You could also have a system with a sigma q that's negative. You would get that way by having more electrons than protons. So if I have 4 positives and 7 negative electrons, then my sigma q is overall going to be -3 coulombs, which I would describe as a larger negative sigma q. So the rest of this slideshow is concerned with the 3 main charging processes. So what I mean by charging is that most objects start with balanced electrons and protons, right? The sigma q is 0, but there are ways that we can manipulate these systems so that we can move our electrons around. If we move them in or out of the object, then the sigma q of that object or the system is going to be changing. One little note, protons can't move, they're stuck in the nucleus. So in all of these examples that we're going to talk about, you'll notice that the only particle that's moving is the electrons. If we move protons, then we're talking about nuclear explosions. So leave the protons where they are, and charging is always accomplished by either adding or subtracting electrons. The first kind of charging I want to talk about is known as friction charging. As the name suggests, this happens when you rub objects together. Friction charging only works with insulators, and we'll talk about why in class a little bit later on. But the idea is that when you rub two different insulators together, electrons can be transferred from one into the other. This is really common in the real world. For example, if you've ever rubbed your feet on the carpet and then gotten charged up and shocked other people, you were doing friction charging without knowing it. So the way friction charging works is we start off with two insulators that are neutral. You'll notice that these two things shown, the green one and the orange one, have the same, each one has the same number of protons as electrons. So the sigma q for each of those objects is 0. When you rub those things together, one of those insulators grabs electrons from the surface of the other one, okay? So you'll notice that in this case, the orange insulator has pulled 5 electrons off of the green insulator, and they're now kind of on the surface of the orange insulator. If you add up the sigma charge now, you'll discover that the green one has 5 extra protons, so its charge is positive 5 coulombs, and the orange one has gained 5 electrons, so it now has a charge of negative 5 coulombs. I will point out that the total system of both of these objects is still neutral. We have still the same number of electrons and protons overall. We didn't create or destroy any of those things individually. So how do you know which object is going to grab the electrons? Well, it depends on the properties of that material. And it's just been determined experimentally. Scientists have gone and rubbed a bunch of things together and discovered which objects grab electrons from others. So they've created something called the Electrostatic Series, which shows you in general which objects end up negative when you rub them and which objects end up positive. So rubber tends to end up negative. That means that most rubbers really love electrons, so when you bring them close to another object like fur or wool or glass, the rubber ends up stealing the electrons from the other insulator. The other end, the positive objects, tend to not be attracted to their electrons as strongly, and so they tend to lose electrons, which means they end up positive when they're rubbed. The second kind of charging is called contact charging. So contact charging has to happen between two conductors, so it's different than friction charging. And the other thing that's different about contact charging is that at least one of the conductors has to have some unbalanced charge to start. So somebody already has extra electrons or extra protons. And if you have that, when you bring those two conductors into contact, the electrons are going to flow back and forth because they're conductors until they're evenly distributed or balanced between the two conductors. You've experienced this in your life as well. In that last example, the friction charging was the socks rubbing on the carpet, but then if you went and touched something metal, for example, since you're a conductor and the metal is a conductor, you end up shooting electrons either onto you or off of you in contact charging when you made contact with that metal. The way this looks at the subatomic scale, you've got these two conductors that start with different amounts of sigma q. On the left, we have a positive 6 coulomb conductor. It's got 3 more protons than electrons. And on the right, you've got a positive 2 coulomb conductor, so it's got 2 more protons than electrons. When you touch them to each other, those electrons are going to spread out. They don't like being piled up on that right conductor. They'd prefer to be over on the left conductor where they've got a little bit more space. So when they spread out and balance out, what happens is you end up with the same sigma q. If we had a 6 and a 2 before, we balance out so that each one will have 4. You can also take the average of the original sigma q to find what the sigma q after is going to be. You ought to also be able to tell how we obtained that final charge. So if that conductor on the left, the blue one, went from a 6 to a 4, the way an object would do that, the way an object's charge would become less positive is by gaining 2 electrons. And you'll notice on the green conductor, we went from a 2 to a plus 4, so we became more positive. And the way we became more positive was by losing 2 electrons. So you can see conservation of charge there. You can see where one object gained electrons, the other one lost them, but in the whole system, we've kept the same amount of charge overall. The next process I want to talk to you about is related to contact charging, but it's a little bit different. It's something called grounding. Um, Grounding is intentionally connecting a conductor to the earth. And you would do this with some sort of wire. If you've ever looked at your outlets at your wall, you'll notice they have three little holes in them. That bottom one is a ground wire. It's literally a wire that goes into the outlet, and then it comes out of your house and it's drilled into the ground outside of your house somewhere. So that wire is actually connected to the ground. The reason we would ground things we'll learn about in the next kind of charging, but in general, the Earth is a massive neutral object, and it's really useful sometimes to provide a place for electrons to go, or a place to get electrons when you're trying to keep charges from being too crazy and unbalanced. So grounding basically means connecting an object to the Earth so that electrons can flow to or from the Earth. The third and final kind of charging that we're going to teach you about is called induction charging. And induction charging uses some of the processes we learned about earlier, polarization and grounding, to give a charge to a conductor. And one of the cool things about induction charging is that you don't actually have to make contact between the two objects that you're charging. And so it ends up being a really useful kind of charging in the real world. In induction charging, you start with your object that you want to charge. It's got to be neutral to begin, and it's got to be a conductor for this to work. The first step is to bring a charged object nearby. And as I said, it doesn't actually have to touch, it just has to come nearby. And when you bring that object nearby, your conductor should polarize, as that diagram shows, letter B. The third step is grounding, which we talked about in the last slide. So you take that conductor and you connect it to the earth. And the reason you do that is because the electrons in the conductor are trying to get away from that charged object that was nearby. So they actually are going to flow out that wire and go onto the earth, which is further away from that big, scary, negative charged object that is nearby. Step D involves breaking or removing that wire to the ground. So now we're isolating our neutral conductor again. And you'll notice now in step E, even when I take away my charged object, the conductor is left with an unbalanced sigma q because it lost those electrons to Earth. So in induction charging, you're charging an object by forcing electrons to flow onto the Earth, or you could actually do this whole process in reverse by attracting electrons from the Earth onto the object. But in any case, you end up with a charged conductor. So those are the three main types of charging that we experience in the world. And at this point, I'd like you to revisit the essential question, which is, how do objects end up with an unbalanced sigma charge? Hopefully you realize it's dependent on the kind of object, and it's dependent on the scenario, the setup. So there's actually a lot that goes into this. As you guys prepare your summary statements, hopefully you include a lot of the things that you learned in the last several slides. Thank you.